So David is going to start. Today we're going to hear about cross-representational knowledge, connecting fractions and decimals. Looking very much forward to this. Yeah, David, just go ahead and then we'll see.
Okay, well, thank you all for coming early in the morning, late in the evening, as it may be. We'll be speaking about cross-representational knowledge of fractions and decimals today, and the speakers will be myself. Jake McMullen will be presenting work with Halme, who was the original speaker, and then it'll be Ilyse Resnick and Leuven. So I'll begin. See if we can get this right. Can everyone see that okay? Great. Okay, so I'm going to introduce the idea of cross-notation knowledge of rational numbers and argue for the importance of this kind of knowledge to children's understanding of rational numbers more generally. This is work done together with Jake McMullen and Michelle Hurst, so I'll just thank them in the beginning so I don't forget it in the end. So I want to start by reviewing some background that's likely known to most of you. Rational numbers are a uniquely important and uniquely difficult topic in early math education. Two common difficulties are children's poor understanding of the magnitudes of rational numbers and poor proficiency with rational number arithmetic. And these two areas of difficulty are related. Magnitude knowledge predicts individual differences in rational number arithmetic skill, and interventions that aim to improve children's knowledge of rational number magnitudes also lead to improvements in rational number arithmetic skill. Now, a distinctive property of rational numbers is that they're regularly represented using multiple notations, fractions, decimals, and percentages. Most assessments of rational number knowledge have focused on what I'll call within notation knowledge, which is to say, understanding each notation on its own. So for example, a typical assessment of fraction magnitude knowledge might test children's ability to compare and order fractions like 1/4, 1/2, and 3/4. And an assessment of decimal magnitude knowledge might assess their ability to compare and order decimals like 0.25, 0.5, and 0.75. In contrast, I'm going to use the term cross-notation knowledge to refer to children's understanding of relations between notations, such as their ability correctly to compare and order a mix of fractions and decimals like 1/4, 0.5, and 3/4. And the premise of this project is that cross-notation knowledge, though challenging to acquire, might offer benefits to students who do acquire it. And I'd like to highlight two potential benefits of cross-notation knowledge. First, children who have strong cross-notation knowledge could leverage their understanding of one notation to help improve their understanding of the other notation. As an example, a child who's trying to understand why 0.4 times 0.2 equals 0.08 instead of just 0.8 might reason in terms of fractions that 4/10 times 2/10 is equal to 8/100, not 8/10. And so the child would be using their ability to move back and forth between decimal and fraction notations to use knowledge of fractions to help understand decimals. The second potential benefit is that the process of understanding connections or similarities between different notations could focus attention on deeper principles about rational numbers. So for example, a child might notice that the product of 0.4 and 0.2 is less than 0.4, and similarly that the product of 2/5 and 1/5 is less than 2/5. And noticing the resemblance between these two facts could help children understand the more general and deeper principle that for any type of rational number, multiplying a positive number by a number smaller than 1 will give you a smaller answer. So these considerations led us to the following hypothesis, which is that cross-notation knowledge of rational number magnitudes would facilitate learning and doing rational number arithmetic. We tested the following prediction based on that hypothesis, that individual differences in cross-notation magnitude knowledge would predict differences in fraction and decimal arithmetic skill, even when controlling for measures of within notation magnitude knowledge. So testing that prediction was the main goal of the study I'm going to show you. And a secondary question that we examined was whether the effects of within or cross-notation magnitude knowledge on fraction arithmetic would differ from the effects on decimal arithmetic. This was a way of getting at whether the effects of magnitude knowledge on arithmetic are notation specific or not. So we set out to test our prediction by reanalyzing data in 3 existing data sets, which are the ones shown on the left here. And each of these data sets included a measure of either fraction arithmetic or both fraction and decimal arithmetic. And further, each data set included either comparison or ordering tasks involving fractions only, decimals only, and mixed fractions and decimals. And so based on these, we calculated measures of fraction magnitude knowledge, decimal magnitude knowledge, and cross-notation magnitude knowledge, which served as the predictors in our analysis. We used the same analytical approach in all 3 data sets, which was a linear mixed model with arithmetic accuracy as the dependent variable. We included participants' grade as a control variable, but our main predictors were fraction magnitude knowledge, decimal magnitude knowledge, and cross-notation magnitude knowledge. Also, to address our secondary research question, we included interactions of each type of magnitude knowledge with the notation of the arithmetic task, that is either fraction arithmetic or decimal arithmetic, except in the first data set because that data set only included fraction arithmetic. Now, we used Bayesian methods to generate a point estimate as well as a 95% credible interval for each effect in the model. And we considered effects to be significant if their 95% credible intervals excluded 0. We also did the analyses with frequentist methods. We got very consistent results, which I don't have time to show today. So I'm only going to show the results from the Bayesian analysis. All right, so let's look at the results. What I'm showing here are the findings from the first study, which involved 4th to 6th graders in Finland and included fraction arithmetic only. The chart is displaying the estimated effects of fraction magnitude knowledge, decimal magnitude knowledge, and cross-notation magnitude knowledge on fraction arithmetic. And the most important point to notice is that there was a significant effect of cross-notation magnitude knowledge on arithmetic as predicted. Decimal magnitude knowledge also had an effect. However, while controlling for both cross-notation and decimal magnitude knowledge, fraction magnitude knowledge did not predict additional unique variance in fraction arithmetic. That's actually a pretty striking finding. Remember that the outcome measure was fraction arithmetic, and so you might predict that, if anything, fraction magnitude knowledge should be the best predictor. But in fact, it was the only one of the 3 measures that did not uniquely predict the outcome. Here now are the results from the second study. This study involved 4th to 7th graders in the United States and included both fraction and decimal arithmetic, which I'm showing in the blue for fraction arithmetic and in the green for decimal arithmetic. However, it included only addition, no other arithmetic operations. So here we once again found an effect of cross-notation knowledge when controlling for both forms of within-notation knowledge. And the effects of cross-notation knowledge on fraction arithmetic and decimal arithmetic actually did not differ significantly, although these effects look different. In fact, the interaction was not significant. In this study, neither fraction nor decimal magnitude knowledge had an effect on the arithmetic outcome when controlling for each other as well as for cross-notation knowledge. So in other words, cross-notation knowledge was the only unique predictor of arithmetic accuracy in this case. And there also were no significant interactions involving fraction or decimal magnitude knowledge, indicating that fraction magnitude knowledge didn't predict fraction arithmetic more than decimal arithmetic, nor did decimal magnitude knowledge predict decimal arithmetic more than fraction arithmetic. Finally, here are the results of study 3. This study had the largest sample. It was with 7th and 8th graders in the United States, and it also had the most complete measure of arithmetic, including all 4 arithmetic operations with both fractions and decimals. So once again, cross-notation magnitude knowledge had a significant effect on arithmetic accuracy while controlling for both forms of within-notation magnitude knowledge. And once again, the effect on fraction arithmetic, didn't differ from the effect on decimal arithmetic. Decimal magnitude knowledge also independently predicted arithmetic accuracy, and this effect, again, didn't differ between fraction or decimal arithmetic. And as in the previous two studies, fraction magnitude knowledge did not independently predict arithmetic while controlling for decimal and cross-notation magnitude knowledge, nor did the effect of fraction magnitude knowledge differ between fraction and decimal arithmetic. So in summary, the principal conclusion from this work is that cross-notation tasks appear to capture aspects of individual differences in rational number knowledge that aren't captured by within-notation tasks. And the effects that we found appeared among children of different ages and nationalities and with different measures of arithmetic. And further, we found that the effect on fraction arithmetic didn't in any case differ from the effect on decimal arithmetic. So we don't know exactly which aspects of rational number knowledge are especially well captured by cross-notation tasks, but I'd like to propose two possibilities here. The first possibility is that cross-notation tasks are measuring children's understanding of equivalencies between fractions and decimals. So for example, if a child is asked to compare 0.5 and 1/4, they might transform 0.5 into 1/2 and then compare 1/2 to 1/4. Alternatively, they might transform 1/4 into 0.25 and then compare 0.5 and 0.25. But in either case, the child would be relying on their ability to translate between fractions and decimals, and the task would be in part assessing that ability. The other possibility is that cross-notation tasks are measuring children's mental representations of analog magnitudes corresponding to fractions and decimals. In other words, rather than relying on a mapping between fractions and decimals, children might be mapping both fractions and decimals to an underlying non-symbolic representation. In this case, when comparing 0.5 to 1/4, the child might map each of them onto some analog representation, which I'm representing by these colored bars. These are intended to represent mental representations of magnitude, not external diagrams. And having made that mapping, a child could then compare the analog representations to each other in order to do the task. So we don't think the current findings enable us to distinguish between these two possibilities. We'll need further research to find out exactly what it is that cross-notation magnitude tasks are measuring that isn't fully captured by within-notation tasks. A secondary conclusion is that the findings argue against notation-specific models of relations between magnitude knowledge and arithmetic with rational numbers. And what I mean by a notation-specific model is a model in which decimal magnitude knowledge is specifically related to decimal arithmetic, and fraction magnitude knowledge is specifically related to fraction arithmetic. In other words, your knowledge of different notations is relatively compartmentalized. But despite the intuitive appeal of this kind of a model, our findings are not consistent with it. Instead, what we found was no evidence for notation specificity in the relations between rational number magnitude knowledge and rational number arithmetic. Decimal magnitude didn't ever predict decimal arithmetic more than fraction arithmetic, and fraction magnitude knowledge didn't ever predict fraction arithmetic more than decimal arithmetic. So the results seem to us instead consistent with the notation general model, in which both decimal and fraction magnitude knowledge primarily tap into a general understanding of rational number magnitudes, which in turn is related to both decimal and fraction arithmetic skill. So I'm going to conclude there. I'd like to thank you very much for your attention, as well as the National Science Foundation for supporting this work, and I look forward to your questions. And somehow I'll figure out how to stop screen sharing. There we go. Okay, so we have perhaps 1 minute for questions as the next speaker gets set up.
Hi, can I ask a question?
Yeah.
Yeah, very interesting work. I wonder if I missed this, or if you can speak a little bit more about what kind of tasks did you guys use for the magnitude understanding for both the within notation as well as the cross notation. And a second question is for the cross notation magnitude understanding. Do you think it can be actually tapping onto whole number division knowledge, which is also a kind of arithmetic that you have to use when you translate a fraction into a decimal? And can that be explaining what you're trying to see here, that the cross notation magnitude knowledge has this unique prediction for the arithmetic?
Yeah, thank you for those questions. That's very interesting. So to answer the first question about how we measured magnitude knowledge, we set out to find data sets that had used either a comparison task or an ordering task or both, with both fractions and decimals and fractions and decimals combined. So it was different in the different studies, in some cases comparison, in some cases ordering, and in some cases both. I think the proposal about division is really interesting. I think of division as one way of mapping between fractions and decimals. So if you're asked to convert a fraction into decimals, one way to do so, if you don't just have it memorized, is to divide the numerator by the denominator. So I think that's very plausible, and I would think of it as a subset of the first of the two possibilities that I proposed of fraction decimal equivalencies.
Yeah, David, I have a question.
Sure.
So very interesting talk. It raises questions about the generality of this understanding, because the two cases that you raised are only two in a very large space. So two that I'm curious what your thoughts are about. One other possibility is third variables that have nothing in particular to do with magnitudes, but rather are domain general kinds of variables that have been found to be related in other experiments to magnitude understanding, such as working memory and spatial understanding. And a second kind of question that does have to do with magnitudes, but also generality, is what about whole number magnitude understanding? Because this may not just be a cross notation effect for rational number magnitudes, but perhaps for all kinds of magnitudes. So those are the two questions.
Yeah, thank you very much. I'm not going to be able to give a very complete answer in a brief time. I think that the question about domain general competencies, I think we know that, for instance, working memory and inhibition are predictors of fraction magnitude knowledge and decimal magnitude knowledge alone. And so in a certain sense, to the extent that each of these measures of magnitude knowledge is driven by domain general competencies, then none of them should be unique predictors when controlling for the others, because presumably those domain general competencies are contributing to all of them. It might be the case that some of them are better measures of domain general competencies than others. For example, cross-notation knowledge might be more sensitive to those domain general differences than the other measures, in which case we would see the effects we found. So we certainly can't exclude that possibility. So with regard to the whole number magnitude knowledge, we know that it's, from other studies by Nancy Jordan, for example, that whole number magnitude knowledge is a good predictor of fraction magnitude knowledge in longitudinal studies. So I think, yeah, I'm not sure I have a great response for that right off the bat. I think there's probably some degree of common skills involved in doing comparisons and orderings, as well as number line estimation, which we didn't include in the current study. I guess what we're interested in is what's the unique aspect for the cross notation task. I think similar to what I said about the domain general competencies, to the extent that these are all sharing similar abilities, be it domain general competencies or general magnitude knowledge. In either case, none of them should be unique predictors when controlling for the others. So there has to be something unique, at least about the cross notation and decimal magnitude tasks from the present findings, if that makes sense. Yeah, thank you very much. And I think we'd better transition to the next speaker, which is Jake. So Jake, feel free to take it away.
While Jake is setting up his slides, I quickly want to apologize for the blinking live button at the top. Hope this is fine now. Mina told me that she fixed it with a paper covering it. So if this happens anytime in the future, you know the solution now.
And maybe it inspires some people with some attention tasks or something like that for future studies to have that there, you know. Yeah, so thank you, David, for your talk. It's really helpful to go after you because this work has sort of, that I'm going to present here, has been inspired by our previous studies and starting to look at this cross-notation idea, which is, of course, the whole reason why this symposium exists. I used a different term here, but I think that it really is related to this idea of cross-notation knowledge and skills. I used representational flexibility in my abstract with rational numbers, but basically we can think of this as the cross-notation knowledge, and looking at this sort of from a little different perspective in terms of other different types of tasks that are measuring this. And this is together with my colleagues from the University of Turku and Tampere. I won't name everyone here, but you can see those names there. Yeah, so the basic theoretical premise that from the perspective that we're looking at this idea that there are these two types of expertise that have been looked at for the past 30 years in research on math and other topics. The idea that there is this idea of routine expertise and adaptive expertise, and that these can be differentiated in some way. And the work by Hatano and Barudi kind of defined this routine expertise as being represented by static and inflexible knowledge that can only be applied in typical situations that have been often practiced. And that while this is foundational knowledge and useful and important to develop, it's not necessarily a desired end of mathematical curricula. And instead, we should aim for developing in students this malleable and fluid adaptive expertise, which involves integrating procedural and conceptual knowledge into novel situations, such as future learning. So being able to use your knowledge flexibly, for instance, in everyday life, but also being able to, for instance, use your rational number knowledge in new contexts such as algebra and later mathematics. And you can see how this could relate to the idea of, for instance, this cross-notation knowledge in terms of maybe most instruction involves teaching about fractions separately and decimals separately, but then being able to use them and move between them fluidly and as the situation kind of requires could be seen as a little bit more adaptive. It's important to note that while routine expertise is foundational for adaptive, it's not just simply that there is sort of more routine knowledge that goes into this adaptive expertise, but rather that there's sort of qualitatively different, more connected, more malleable knowledge. And this has been looked at in the field of mathematics development in a number of previous ways. Notably, for instance, Andauker looked at this in the early 90s with this idea of how math experts solve mental calculations using these friendly numbers and are able to kind of work between the numbers in creative and new ways. This has been looked at a lot in the field of procedural flexibility, in particular in algebra and arithmetic. And my colleagues' own work has looked at the idea of what we call adaptive number knowledge with whole numbers and rational numbers. And adaptive number knowledge is defined as the well-connected knowledge of numerical characteristics and arithmetic relations. And this again, is my connection all right? I feel like I just lost everyone for a second.
Yes.
Okay, good. Yeah, so the idea here is that students kind of integrate their conceptual and procedural knowledge in these novel contexts. And we found that, for instance, it's related to but distinct from procedural and conceptual knowledge, and that it predicts later algebra even after taking into account this sort of more routine knowledge. The main task we've used so far to measure this is what we call the arithmetic sentence production task. And here is the example of the rational number version of it, where they're given 5 numbers and have to come up with as many arithmetic sentences that equal a target number in a limited amount of time, 90 seconds to 2 minutes. And you can see that here in this rational number version, for instance, we use equivalent fractions and decimals. So we have both 1/2 and 0.5. And what we found that this was distinct from sort of routine, procedural, and conceptual knowledge. And one way we discovered this was using a latent profile analysis. And what we found, if we focus on just the top two profiles here, these top two lines, is that among students who have strong conceptual and procedural knowledge, these first four indicators, they're fairly equivalent there, but there's a large distinction in their adaptive rational number knowledge. So we see that at the upper levels, they're even and what we found when we looked at these students in these different profiles, the type of solutions they offered on the arithmetic sentence production task, we found some interesting patterns. So one thing we looked at was their percentage of mathematically equivalent solutions. So if you recall, there was both 1/2 and 0.5. So we looked at how often they used the exact same arithmetic relations to find the solution number, but they used then differing representations. So for instance, if they had 1/2 plus 1/4 plus 1/4, then they also had 0.5 plus 0.25 plus 0.25. And what we found was that this quite clearly aligned with their overall performance levels on the adaptive rational number knowledge task. So the lowest students only did this about 10% of the time. The students who had strong routine knowledge did this about 1/4 of the time. And the students who performed best did this about 1/3 of the time. What we also looked at was when their cross-notation solutions. So there we found that this aligned more with their overall conceptual knowledge. So you can see sort of a distribution there that for instance, the students in the lower groups, they had less than 10% of solutions that used both fractions and decimals. But the students in the upper groups, both of them had roughly 1/4 to 1/5, and that more aligns with their sort of conceptual knowledge patterns in this task. So what we're looking at today is in a different data set. We want to look a little bit more closely and see what kind of cross-notation knowledge is related to these types of solutions on the arithmetic sentence production task. So in general, trying to look and see across various task types, what kind of cross-notation skills and knowledge do students have and how are those related? So this was a study with about 200 7th graders in Finland. They came from 13 classrooms. This was the pretest from an intervention that we carried out trying to improve overall their adaptive rational number knowledge. But we're just looking at sort of their performance across the various measures on the pretest. We carried this out in the classroom, a whole classroom setting, and used computer-based tests. So the measures we included, we're looking at today are both cross-notation measures and within-notation measures. The cross-notation measures included the mathematically equivalent solutions and cross-notation solutions on the arithmetic sentence production task. They included the fraction and decimal conversion. So just simply, we gave them a fraction, write that as an equivalent decimal. And finally, cross-notation ordering. So like David described here, they're given 4 decimals and fractions and have to put them into order from smallest to largest. The within notation measures, they just had simple one-step calculations, so 1/2 plus 1/4, and there were 6 that involved fractions and 6 that involved decimals. There were no cross-notation ones here. And then they had number line estimation. Again, these were within notation because it's number line estimation. So put a fraction on the number line where it's supposed to go. And then within notation ordering. So then just they had 4 fractions, put those in order, 4 decimals, put those in order. And what we found was in general, unsurprisingly, everything was highly correlated or fairly highly correlated or moderately correlated. All of these correlation values are significant at a point less than 0.001. And I don't want to spend too much time trying to pick these apart. Maybe there would be something interesting to look at in terms of whether or not there's cross-notation differences between cross-notation and within notation. But what I wanted to mainly do today is look at how these different skills predict their performance on the adaptive, the arithmetic sentence production tasks. So we'll just go ahead and go there. So first, trying to predict their use of equivalent solutions on the arithmetic sentence production task. Put in a hierarchical regression, first inputting the within notation knowledge and then the cross notation knowledge. And what we find is that for equivalent solutions, both within notation and cross notation uniquely predict equivalent solutions as a whole, that their R-squareds when entered at the last step, the change in R-squared was, well, 0.06 for both of them. And we see, if we look at the betas, that the conversion task was the strongest predictor, or the strongest relation with equivalent solutions. So this sort of explicit ability to convert between fractions and decimals was the strongest. And then cross-notation ordering, calculation, and number line estimation all had pretty weak relations. And overall, this explained about 43% of the variance in the use of equivalent solutions. So a good chunk of that variance, I would say, is explained there, but still a lot unexplained. And then for the cross-notation solutions, we see a different pattern overall. Here we see that the within notation knowledge doesn't uniquely predict the use of cross-notation solutions, whereas the cross-notation knowledge does. Again, conversion was the strongest predictor, and cross-notation ordering was the only other significant predictor, and then the within notations were all weaker. Yeah. So in conclusion, from previous research, our own research seems to suggest that this cross-notational knowledge might be important for adaptive rational number knowledge in general. The present study suggests that explicit cross-notation knowledge only partially explains overall. Sorry, just to point out that the total R-squared for cross-notation solutions was actually only 0.31. And considering this is 5 measures of rational number knowledge, I would say that that's lower than I would expect. So overall, this is kind of not explaining a lot of variance in the use of cross-notation solutions on the arithmetic sentence production task. And yeah, there is some evidence also that within notation knowledge is explaining a bit of the use of these cross-notation features, in particular with the equivalent solutions, but not necessarily with the sort of cross-notation solutions themselves. But in general, I think this still falls in line with our own understanding of the arithmetic sentence production task and the idea that they have to integrate multiple aspects of their knowledge. In this case, this cross-notation knowledge seems to be one component of that is important, but it's clearly not the only thing that is important in order to be successful on that task. And this is, again, in line with theories of adaptive expertise, which suggest that you need to be able to bring together multiple features of procedural and conceptual knowledge and integrate them into sort of a new solution strategy on this novel task. But of course, there's open questions. So I think that this question of how it's important is still should be a question mark behind it. I'd want to explore this further and looking, for instance, at a version of this task that doesn't have equivalent rational numbers. And I think that looking at specifically some idea of cross-notation flexibility, both David's presentation and I think here suggests that we should explore this a little bit more, how students can move between these different notations in flexible and adaptive ways that is probably going to be the most beneficial for future learning. Yeah, and thanks to our funders, and yeah, let me know if you have any questions. I'm always absolutely terrified that I've lost my connection halfway through, but it seems like you're still there. Maybe we have a short question while whoever's next sets up.
Ilyse will be next.
Mm-hmm.
Should I start sharing my screen?
Yeah, go ahead. I think we're falling behind, so it's probably good to move on.
Okay. Let's see. We actually hit play here. So you can everyone see that okay?
Yes.
Yes, good. So thank you for having me. I am going to present on work that I did with Nancy Jordan and Luke and Christina at the University of Delaware when I worked with them there. I'm currently at the University of Canberra, which means I'm based in Australia, and it's around 12:30 in the middle of the night. So just putting some qualifiers out there before I jump in. The data that I'll be presenting was published in the Journal of Educational Psychology. And here we were really categorizing how children reasoned about decimals and fractions, and how that reasoning related to each other and also to later mathematics achievement. So I'm sure you're all aware that, that decimals and fractions are mathematically related, right? So 3 pieces of 10 is equal to 3/10 in fraction form and 3/10 in decimal form. Now, historically, that was reasoning about fractions, say, versus whole numbers or decimals may have been viewed as different separate processes that are with fractions being less intuitive and harder than, say, more continuous magnitudes. And then so the representation, so work by D. Wolf was looking at representations of whole number, fraction, and decimals. And they found that whole numbers and decimals were represented as continuous one-dimensional quantities, right? So thinking about like soda in a soda bottle, or liquid, I should say, in a soda bottle, contrasted with, say, fractions, that two-dimensional relations between discrete objects. So having those 2 numbers there would be more like thinking about candies in a box, right? So there's like parts of a whole. More recently, work is showing that reasoning about, I need to move you guys, reasoning about fractions is actually the same as reasoning about any other kind of magnitude, that it's part of one integrated continuous process where children are gradually expanding their mental number line to include larger numbers and eventually rational numbers. And focusing on reasoning and not just representation, but that the way children and adults would reason about different kinds of magnitudes would be using multiple strategies. Which would include both, like, say, rule-based reasoning, so how do these numbers work, and also those holistic representations, and that you would adaptively choose what strategy you're using based on kind of like mental effort, what is the most efficient way to solve this problem. So just by way of an example, focusing on fraction magnitude, looking at that first say comparison. So is 3/10 larger compared to 8/10? It is really efficient just to compare those numerators because the denominators are the same. So I don't even think about the magnitude of the fraction. I can just look across those top numbers. Contrasted with, say, the second comparison, it's helpful for me to think about 1/2 on a number line because I know it's just right in the middle. And then I just have to put 9/20 relative to that. And so I have different strategies based on the task demands. So we're picking strategies based on efficiency and mental effort. Now, one thing that Nancy Jordan's lab did when they first started the study before I had joined them is they had developed a magnitude comparison task. And so the first one they have is these fractions. And what I want to draw your attention to is that there's different blocks of items, and each block of item has a kind of different quality to it that is going to be aligned with something called a whole number bias. And so that's probably the largest kind of error, but still a strategy that the children are using to say, how should I figure out which of these fractions is larger? I'm going to use whole number properties to help me solve that. And actually that is helpful if the denominators are the same. So if you look at block 2, that's a helpful strategy. They'll actually get that one right. But you would expect them, if they had that whole number bias, to get blocks 1, 3, and 4 incorrect because, 3/7 versus 3/8, just, using the whole number properties there, it would give you the wrong answer. And then on the last two blocks, because it's not really applicable, you would see them perform at chance because they don't really know what they're doing. And so you can kind of anticipate some sort of pattern of response that you would get if the child was using a whole number kind of strategy to answer which one is larger in this comparison task. So that was crafted. And my colleague, so I wasn't on this paper, this was led by Luke, who's on this work here, but he also did this one on another sample of the same longitudinal data set, but it was a different sample of the kids, and it was focusing just on the fraction kind of changes over time. They found a developmental trajectory between 4th to 6th grade that I'll walk us through using this example, which is larger, 1/2 versus 9/20. They found that children in year 4 tended to use whole number properties, right? So they would say, oh, well, 9 is bigger than 1, so 9/20 must be the larger fraction, and they would have gotten that wrong. But eventually they begin to adapt an opposite strategy where they say, oh man, I keep getting that wrong. It must be the opposite for fractions. And so I'm going to pick 1/2 is bigger because 1 is actually the smaller number is the bigger number for fractions. And so they're not really reasoning about the magnitude. They're using rules that they're developing, but partial, but nevertheless rules that they're using to help them figure out what should they do. And then eventually over time in 6th grade, they're, in terms of that kind of, what kind of pattern do they have, you're seeing a more normative pattern of using fraction properties, that they're really understanding that 9/20 is less than 1/2 because it has, less of a magnitude. So the aim of this study then is to categorize 4th grade students' use of this kind of rule-based reasoning around decimals. And our aim here is if they reason about decimals in similar ways to fractions, then we can see kind of similar approaches across representational format, but they're using the same type of approach, same type of reasoning. And we also look then if that reasoning is predictive of fraction magnitude later. And this is actually going to talk to the order of when do we teach fractions versus decimals, because currently fractions are taught first, but that it would be helpful that potentially learning decimals might support fraction learning. So foreshadowing some things, I suppose. And then also looking to see if that rule-based reasoning is predictive of later mathematic achievement. And importantly, in our model, we look to see if fraction, decimal, and whole number all uniquely contribute variance in predicting math achievement later on. If they each predict unique variance, that would suggest that they're at least somewhat separate skills, different skills, versus let's say, fractions came out ahead and the other two aren't as predictive, but you would interpret that as having a lot of shared variance, right? So, are they doing separate things? Or are they doing one thing of just magnitude? And so these are kind of our goals at the onset. So we did this study with, as I mentioned before, with the fractions. We followed around 435 students in this particular analysis from 4th to 6th grade. We assessed 9 elementary schools across 2 school districts that were primarily serving low-income families. So we had a really diverse sample of students. So my procedure, I had to keep moving this. So the procedure was we actually started the study in 3rd grade. And here we had assessed like their demographics, working memory, attentive behaviors, nonverbal memory, reading fluency, receptive vocabulary, and whole number line estimation. And I will talk about some of them later briefly. But really what you want to know is all those kind of background factors we assessed in 3rd grade. And then in 4th grade is when we assessed fraction and decimal knowledge for the first year. And then in other studies, we looked at 5th and 6th grade. But here I'm really focusing on that 4th grade cohort. So we looked at fraction comparison in the fall of 4th grade and again in the spring, and we looked at decimals in the middle. And just to point out, the decimal comparison task was designed much in the same way, where we identified in the literature what are common errors that children make, or strategies really that they're misapplying when they reason about decimal magnitude. One is that whole number bias, again, where they're using whole number properties, and the other is a place value bias. And that's going to be that they don't understand what place value is. Take, for example, the second block. You have 0.04 versus 0.4. If you had a place value bias, you might mistakenly say that 0.04 is larger because there's actually more digits in that number. And so you're really counting the number of digits. And again, you can see that sometimes the whole number bias is going to help you or hurt you, or not really be applicable. And same thing with place value. And I'm going to highlight two in particular, just to really emphasize what's happening here. So in that fourth block, 0.04 versus 0.5, you can see that the whole number bias helps, but the place value bias would hurt. Contrasted with the one below it, 0.06 versus 0.2, both hurt. And so you're going to see differing patterns emerge, but for people who have whole number bias and place value bias versus one, maybe having just one or the other. So that's what we're really looking for, those kind of patterns of responses across all these different items. And then at the end of sixth grade, they took a statewide standardized mathematics test. So we did a latent class analysis, and the latent class analysis, again, is trying to capture what are the different kinds of patterns of responses that we can see. We found 3 distinct patterns, and I have them outlined here, looking at just the decimal one first. And what you found was there was a group of students who were actually really good. And this is probably before they received much decimal instruction at all, but they really had a strong understanding of which one was larger across all of the different blocks of items. Then there was a group of students based on, again, this, we're going to interpret their pattern of response in this latent class, that they show that they have a partial understanding. So these are students who are persisting with a whole number bias, but they actually understand place value fine. So when on those items where it was like 0.04 versus 0.4, they got that one right because they understood place value. It was just that the items that whole number bias would hurt them. They were still using that whole number bias. And then there was a group, our largest group, of poor understanding, where they really still were using whole number properties and a place value bias to really navigate this task. And that in some ways, this is right around when they're really getting this instruction, and perhaps they're disadvantaged kids that we're seeing that large of a number. We see the same type of 3 distinct classes coming out in fractions. So this is really replicating that work by Luke I mentioned earlier, where you have students with a good understanding, students with a partial understanding. So these are kids who are using that opposite strategy. And then those with a poor understanding, which are really persisting with that whole number bias. And so here we're seeing similar ways of reasoning about fractions and decimals using different kind of numerical properties that they're aware of in rule-based reasoning ways. So effects of covariance on the latent class membership. This is saying, what is the membership profile? What's the profile of the different students in the different classes? So if you compared the decimals with a good understanding versus poor, you see I didn't include, just for sake of the slide, I didn't include all the ones that weren't significant. I only included the ones that were. And you see whole number, line estimation, and receptive vocabulary. Receptive vocabulary, we see that really pop up a lot in supporting math and just general academic achievement. But whole number, line estimation, perhaps those good students are really using their sense of magnitude to answer and respond to these questions. And that's contrasted with the decimals poor, partial understanding versus poor understanding, the lower rows, where whole number line estimation doesn't differentiate between class membership for partial versus poor. And so this could be, again, thinking about, well, if they haven't developed that kind of analog representation yet, they're really using rules to help them figure out how to navigate this task. And so and consistent with that interpretation is the nonverbal ability being predictive in this instance, that they're using some amount of logic to figure out what is the correct answer. So decimal understanding supports later mathematics achievement. So in my table here, I just have the decimal classes, so good, partial, and poor. And the y-axis is their performance on that state standardized test. And so you can see a very nice clear, their class membership for decimals is predictive of math achievement. In the same model, we see that whole number line estimation and fraction magnitude comparison are also uniquely contributing to math achievement. So this is suggestive that they're at least in part dissociable skills, perhaps based on that number knowledge of how they each operate. What do I have here? Decimal understanding supports later fraction understanding. So here we did a structural equation model where we put in that class membership of decimals, controlling for the fall fraction. So the previous fraction knowledge, we control for that. Does decimal understanding predict later fraction knowledge? And we see that it does. And so this is going to suggest that perhaps understanding decimals would be supportive of later fraction learning as opposed to fraction learning supporting decimals later. And let's see, so discussion, I kind of put in some interpretation in my presentation of the results, but just again, seeing some sort of learning trajectory between the different papers coming out of this data set, where we're seeing kids develop that thinking and reasoning about magnitude might be a process of learning different rules, which includes partial understandings. And those partial understandings could be really important in some sort of like transitional knowledge, so that, the kids that, I don't know if I mentioned this, but in the fraction paper by Luke, the kids that developed a partial representation were more like, or a partial understanding, were more likely to develop a normative understanding later, contrasted with those who really persisted with that whole number bias. So we're seeing a really important role of that transition, of partial knowledge as transitional. And then going back to the DeWolf findings, that perhaps those older kids, because her paper was looking at older children, perhaps that, and adults, that you would develop that analog representation over time and be able to use that kind of strategically if that, was mentally efficient to do so. But that mathematics achievement would be supported by being able to flexibly apply different sets of numerical rules and representations in different situations. So that flexibility is important. And as I mentioned, thinking about learning decimals first, so to support later fraction learning. I have no idea how I'm doing on time. So I hope I'm okay. But this is my last slide, just to acknowledge everyone that I've worked with, the center, everyone that's helped us collect data, and all of you for your attention on this talk. And that's all I have. Let's see if I can pause here, stop share. There you go.
And since we're rather short on time, I think we'd better jump right to the next presentation.
Sorry, did I go? Sorry.
So you should be able to see my screen, is that correct?
Yes, it's not full screen yet, though.
Yes, my computer is a bit slow. Yes, it's there. Okay. So hello, everybody. I'm going to try to do it as fast as possible because I know we're running out of time. So today I'm going to talk about the collaborative study that I conducted together with Juanma and Sonera from the University of Alicante and Wen and myself from the KU Leuven in Belgium. And it's about learners' understanding of the dense structure of rational numbers. So the positive thing is that I'm the last one, so I don't have to explain my theoretical background a lot. So just very summarize it, that the understanding of rational numbers is an essential part of numerical development. We know that from previous research, but we also know, and I think everybody agrees, that a lot of students and even teachers and adults have a lot of difficulties with rational numbers. And just to show you some examples in Flanders, so this is from a colleague of mine who investigated the rational number understanding of pre-service teachers in Flanders, and these are real answers to this equation, for example, and here they have to fill in the blanks. So here you can already see what Ilyse was talking about, this natural number-based reasoning in rational number items. And this is actually also the main topic of today of my presentation. So of course, there are other reasons why fractions are so hard to understand, but one of them is this natural number bias. This has been given a lot of research attention in the last decade. And this can be explained by the conceptual change theory. So very briefly, in sum, the natural number bias exists because before you enter school, the only numbers you encounter in your daily life, so when you grow up as a child, are natural numbers. You learn to count on your fingers, you learn to count how many nights you still have to sleep before you go to the zoo, etc. So it's all with natural numbers, and this is actually confirmed by the first years of instruction. So also in kindergarten and in elementary school, the first years, when you do something with mathematics, it's almost always with natural numbers. So you create this concept of numbers, which is solely based on natural numbers. And then, of course, when rational numbers are introduced in the classroom, in Flanders, it's around the 3rd grade, then problems and misconceptions occur because the properties of natural numbers are not always applicable anymore for rational numbers. And this is actually what is called the natural number bias. So the natural number bias is a tendency to apply natural number properties in task with rational numbers where this is inappropriate. And the research domain always or mainly focuses on 3 aspects. One is already discussed by Ilyse. So also here an example that 2/5 is larger than 2/3 because 5 is larger than 3. The second aspect is operation. So you can also clearly see here that this student answered this equation based on natural number reasoning, which is of course incorrect. But today I'm going to talk about density. So what is density? It's about the structure of rational numbers. So in comparison with natural numbers who are discrete, so you can always say which number comes next. After 5 comes 6, after 6 comes 7, etc. You cannot say that with rational numbers, which number comes next, because there are always infinitely many numbers in between rational numbers. And this is an answer of a learner from one of my studies during my PhD. And this Dutch means that how many numbers are there between 1/7 and 5/7. You can clearly see that also this learner thinks about natural number knowledge when he or she solved this item. So why is it important to also investigate this density understanding? Well, based on previous research from my PhD, you can see it here, there was a representative sample. We really looked into the strength of this natural number bias in the 3 aspects. So first, for size, you can see here at the y-axis the odds ratio. So the larger the odds ratio, the larger this natural number-based reasoning is. We compared it for size, operations, and density from the 4th grade until the 12th grade. And if you look at the y-axis, you can clearly see that with density, the odds ratio is much larger compared to the operations and the size. So it's really a clear issue and that not a lot of students have a good understanding of this dense structure. So that's one reason. Another reason is another study that I conducted together with Jake, who was the second presenter today. A longitudinal study in which we followed learners for 3 years, and latent transition analysis in this study showed that actually the fraction density understanding is a better predictor for algebra performance than fraction size understanding. So in sum, it is an important predictor of later mathematics, such as algebra, but it's also a really stumbling block for many learners. So what was the aim? Oh, another slide. So from the conceptual change theory, we know that to overcome this natural number bias, that we need a conceptual change to get to this good understanding. And from other topics in the conceptual change literature, we know that this is not always an all or nothing issue, but it's a very gradual and time-consuming process with several intermediate states. So it's not that at one day you have this naive idea of a concept and the next idea you have a perfectly good understanding. It's a lot of time with intermediate states. So the aim of this present study was to really characterize these different stages from a naive to a correct understanding of the structure of rational numbers. And also at the second step, we also wanted to look at the difference between conceptual and procedural understanding of this density. So what were the participants? We had quite a large group from the 5th grade until the 10th grade from 10 Spanish schools. And the instrument, we used 2 types of items. I have to say this is part of a large project. Today I'm focusing on these 2 types of items. So the first type of items are the question items, and these were all items where the question was how many numbers are there between, and then numbers such, yeah, with decimals and fractions. And this is what we consider as conceptual understanding. So really understanding that there are infinitely many numbers in between two rational numbers. While other types of items that has been used to investigate this understanding of density, and I also myself used it and puts the sum score of both question and right items as density understanding. However, we think that these right items, so where you have to really write a number between two different numbers, are more, yeah, investigating the procedural understanding of density. So if we look at some results, because I don't have the time to show them all, we did profile analysis on both these conceptual items and procedural items. And the first thing that we see is that also here, there are indeed several intermediate stages of understanding. So it's not an all or nothing issue, because if that would be the case, then we would only find learners who have a naive profile of density and learners who have a correct profile. But you can see that both with the conceptual items and procedural items, we found several, yeah, other types of profiles of learners. If you then look at the yellow circles, what you can also see here, and this is really the topic of today's presentations, is that there's a difference between decimals and fractions understanding of this density. So this profile of learners, these learners have already a good understanding of the dense structures of decimals, but not of fractions. So they understand that there are infinitely many decimals in between two decimals, but that there are no fractions in between two other given fractions. Then what you can also see if you look at the blue line is that there's a clear evolution. So the naive profile, so who always answer here that there are no numbers in between two numbers, and here that they cannot give another number in between two numbers, you can see that it really decreases going from the 5th grade until the 10th grade. However, it is still present at the end of secondary education. So what we can also see is that there is more naive procedural understanding if you compare it to conceptual understanding. So this group is much larger compared to this group. And in the same line, what you can also see if you look at the green circles, that's the group of learners who have a correct understanding, so who can say there are infinitely many numbers in between two given numbers, are much larger than the group that can really say this is a number that lays in between. So there's a clear difference between conceptual understanding this and to procedural give you a number in between. Then lastly, we looked into, okay, so how many of those learners who say can correctly understand that there's infinitely many numbers in between can also give a number. This is only a bit more than 1/4. So that's really not a lot. So if I can summarize all this data, we can say that the idea of discreteness remains strong even in the last grades of secondary school. And this is actually in line with previous research. So this is always said, but it's actually also very important that there should be awareness of this inappropriate natural number-based reasoning in instruction. We also found that there are several intermediate states of understanding. So this means that it's not an all or nothing issue, also not for density. And we also found that there's a clear difference between conceptual understanding, this dense structure, and the procedural understanding. So this is important when we want to provide adaptive instruction. Then we found that students first understood the dense nature of decimal numbers and then of fractions. So we found a group of learners who already understand this for decimals, but not of fractions. And this means that not all learners yet treat fractions and decimals as the same set of numbers. And this is actually important. And I think the previous studies showed this. So from the previous speakers, they already pointed to this importance of cross-notation knowledge. And this is actually also important to see here that this is actually also causing problems in understanding the density of rational numbers. So to end with some suggestions for further research, of course, this is based on cross-sectional data. So longitudinal data is much better to really look into this evolution of the profiles. So longitudinal studies can look at the transition path. So is it the case that all learners go through the same profiles from the naive to the correct understanding or not? And qualitative studies can really help us to look into the reasoning processes of the learners. So thank you very much. If you would have questions, given the limited time that you cannot raise now, you can always contact me or the first author on this mail address. So thank you very much.
So I have a question. As dim as the picture of rational number understanding is that comes out of your work and that of many others, a lot of whom are here, it still may be too optimistic, because I really wonder, there was a piece of data that you mentioned but passed over very briefly, which was that only 28% of the people who said there was a infinite number of numbers between the two decimals, I believe so, it may have been the fractions, actually could provide an example. Now, you have to wonder whether these people understand the concept or whether they're just parroting something that they heard somewhere along the way. Because if you can't generate any examples, in what sense do you really understand the concept?
Yeah, I agree. And that's something so we are writing the paper on this study at the moment. And that's something that we really want to also highlight in the discussion, that this is very important to look at this, because in previous studies and also in my own studies, I admit that we put everything all on the pile together. And we said if they can say, okay, there are infinitely many, that they understand this. But clearly it shows that if you then ask to give them a number or to give at least one number in between, that a large group of these learners who say there are infinitely many cannot do that. So you have a good point there that this is indeed the case. Is that an answer to your question?
Yes, no, that's fine.
Yeah.
Okay. Any other questions left for our speakers?
I don't have a question, but maybe a remark or maybe a question. It's mostly related to Ilyse's talk. And it's something that I've been thinking about already also for years to maybe do research about. It's the role of language, because if I also hear David talking, if you see decimal numbers and it's 0.25, you say it's apparently in English 0.25, but like if I translate it from Dutch, we would say 0.25. So I think language is also a very, it plays a big role in decimal understanding and also this natural number-based reasoning, because we say really 25. And I can imagine that in this case, when Dutch learners are seeing decimal numbers, that maybe this natural number bias plays actually even a more or a bigger role compared to a language where you really say 25. But that's just a remark. It's not really a question. Yeah.
Yeah, I agree with you. I know there are some studies that look at that. I think it was like based in China, where they have more explicit knowledge, explicit language around like 11 to 20. That say it's like, tens or something, that find exactly what you're suggesting. So that'd be good. How do you say 0.04?
Yeah, 0.04. You would say 0.04. Yeah.
But you say the zero, you don't say point, or you explicitly point out the zero is still there. So it is differentiating, but it's not necessarily pointing out that that's sort of at a different level.
No.
So it's 0.04 versus 0.25.
Yes.
Yeah, cool.
Dutch is a fun language.
Yeah.
Yo, can you clarify again, when you asked them did you ask them to find or calculate a number between the two numbers, or to just name one?
To just find or name one. So
but it was sort of name.
Number.
It wasn't like, can you calculate a number between these two numbers, or something sort of like almost more procedural in nature. It was still sort of a declarative question, or I don't know, I guess it was in Spanish, so you might not.
Juanma, can you help me with whether it was, Juanma is here, so the first author, whether in Spanish it was more procedural or not, but in Dutch we would write, we would ask just write a number.
Yeah. Right. I think but I wonder if that would make a difference if you would sort of make it a more active question, like.
Yeah.
Yes, the question was just to write one number in between. So that's more or less the one that appeared in the PowerPoint. So
Okay, thanks.
I don't know. I didn't understand exactly the question. What is the difference? What do you think that was the question?
Well, it was more if you would find a difference in how students respond if you kind of gave them a more active prompt. If you said, for instance, calculate a number between, somehow instead of, or even maybe find in comparison to write, where they.
Just give me an example. If you consider that it's possible to write one, or if you consider it is impossible, just say impossible.
Yeah, it would make it more procedural.
Yeah.
I agree. Yeah.
But it's not a typical procedure that they learn at some point anyway, so it's not like they, are going to rely on some algorithm necessarily. They would still be.
That's true. Yeah.
All right, then. There is no more questions for today. Thanks for staying longer, everyone who stayed. Thanks for your presentations. It was lovely symposium. And see you all next week. I believe it's our late night, isn't it? Let me just check. Anyways, you'll get an email. Thank you very much, everyone. Bye-bye.
Thanks, everyone. Bye.